Hello. Today we're going to talk about economic growth. We're going to talk about a few basic facts about economic growth that will then inform us as to how we should build a model that delivers economic growth. This is going to build on what we've done before, which I referred to as the basic growth model. However, in that model, those of you who have prior experience may have noticed that there's no mechanism in there to generate economic growth. In other words, we're going to have to add something to the model. One thing we're going to have to add to the model that's going to generate economic growth is productivity change. We'll see that although in general the production functions are going to have constant returns to scale, this is not going to be enough to generate economic growth because, of course, one of the variables that we have there, the amount of labor, doesn't grow over time. At least not so far, if we have a fixed population. Now we see that if you have a growing population, it's still the case that we'll have decreasing returns to scale in capital, in the one thing that we're able to reproduce reliably, if we think of population as something that changes exogenously. There are models of endogenous fertility, but that's something for the future. So if we take the population as something that grows exogenously, we will see that we'll have decreasing returns to scale in capital, and that means that you just can't grow by accumulating more and more capital. At some point, it's too costly. In other words, you need something that improves the efficiency of labor and capital in your economy, and that, of course, is some sort of productivity change. As I've implied, we'll also want to introduce population growth into this model, just as a matter of realism. So today we're going to look at how macroeconomists tend to introduce productivity change and population growth into the model, and what kinds of restrictions on utility functions and production functions are going to be necessary in order to get sustained growth. Let's have a look. First, we're going to look at a couple of things that we're going to refer to as stylized facts. These are general features of economic growth that we're going to take as given that are going to help us when we're trying to figure out how we should model economic growth. And these facts are sometimes known as the Kaldor facts. The first one is what we see here, which is that the rate of economic growth doesn't seem to display any clear trend upwards or downwards over long periods of time. The blue line here is economic growth rate measured quarterly in the United States, but annualized. And so we can see that it fluctuates all over the place. But the orange line, which is the average growth rate since 1947, goes through most of this. So there's no obvious trend upwards or downwards. The more eagle-eyed of you might think that we seem to be spending an awful lot of time below the average out here, and that's true. The average here, historically, the orange line, is at 0.019, so that's 1.9% growth in GDP per capita, real GDP per capita. Whereas since 2008, the average has been 0.009 or 0.9%. So indeed, we haven't been having a great decade, and that would be an interesting research topic. So that's the first stylized fact. A second stylized fact that we're going to build on is this one. This is the share of GDP that goes to labor. So it's labor income divided by GDP in the United States. And the stylized fact that we're going to use is that this share does not have any trends either. Now, if you look more closely at this, you will see that there does kind of seem to be a trend here, even if it's a gentle trend from around 0.64 to 0.6, but still that's something, even if it's gradual and took 64 years or so. But we will take the stylized fact as given that this share doesn't really change significantly. And then again, the fact that there seems to be, at least recently, a possibly downward trend in the source of labor income is an ongoing research topic. Some people argue it's due to mismeasurement. Some people argue that it's due to outsourcing and international trade, or maybe the increased use of robots, or maybe it just reflects increased market power by the largest firms, who then take a greater share of their revenue and a smaller share goes to the workers. We'll see. That's an interesting research topic for the future. So those two stylized facts are going to be very important in us developing a growth model. Now, let's start with the growth model. So we're going to have to be very careful here, because remember, we want to have population growth. So we need a model with a growing population. So how are we going to have population in here? First, we're going to have the population starting with a continuum of mass 1. So that means the number of people when we start off is 1. Now let's assume that it grows by a factor gamma sub n. So that means the population each period is gamma sub n to the power of t. Great. Since we have a growing population, we're going to have to be very careful to distinguish between per capita variables and aggregate variables. So per capita variables will be lowercase, and aggregate variables will be uppercase. All right. So previously, we had that the agents were households, and they maximized this, the discounted utility of consumption. Now instead, we're going to say that we have a continuum of dynasties. In other words, these are households that may grow over time in terms of the number of people they have. They all grow at the same rate. The rate, of course, is gamma n. And what they maximize now is the weight, is the sum of the utilities of each of its agents. So little ct here is the consumption of each member of the household. And of course, the sum is just this times gamma n to the t. So the population kind of ends up entering here in much the same way as the discount factor. Now, if you remember, in order for the value function that we get out of this to be a contraction, we're going to need the property of discounting. So we're going to need this product, beta times gamma sub n, to be strictly less than 1. As we'll see later, in fact, we're going to need an even more strict condition on parameters to make sure that we have something that works here. Anyhow, going forward, the agents are maximizing this subject to their constraints. And so we're going to go with the planner's problem here. Remember that the planner's problem and the market problem have the same solution in the end, just takes a bit longer in the market case. So what are the uses of output here? The uses of output are going to be consumption. So this is now aggregate consumption of the whole household, and investment. Notice I'm using uppercase now. And that must be less than or equal to total production, which will depend on total capital and total labor. The next constraint is the capital accumulation function. So big KT plus 1 is the undepreciated capital left over from the past plus total investment. And previously we had that labor N was between 0 and 1. But of course, now we have a growing population, so instead of being between 0 and 1, it's going between 0 and 1 times the number of people, which is gamma N to the T. Or to put it more simply, it's going to be drawn from this interval. And again, because we don't have leisure here in the utility function, that means that N is going to equal the maximum, because there's no point not working if you don't get any enjoyment out of it. The reason we're doing that is because we're interested in long-run growth, and I guess another feature of the data that I didn't show you, but which is also true, is that employment to population ratios also don't seem to have much of a trend. So we ignore the determination of that, since what we're really interested in is just understanding growth, at least right now. If you're interested in understanding employment dynamics, of course, you would want to put leisure in the utility function. Great. So there's one change that we need to make, because what we're typically going to do is we're going to say that this thing has constant returns to scale, this production function. And now one thing I was saying outside there in the garden was that when this production function is constant returns to scale, you're not going to be able to get long-run economic growth just by accumulating capital. And here's a very simple example to make that clear. Let's suppose that we have the Cobb-Douglas production function. And let's plug in the fact that labor is a known quantity here. Sorry. Right. Labor is gamma to the T. And so this is what we have. What's this going to look like when you increase the amount of capital over time? Well, actually, let's put it another way. Let's divide this by the population, because then we're going to get GDP per capita. So GDP per capita is equal to this divided by the population. And what are we going to end up with? We're going to end up with this. So to simplify, GDP per capita is going to be this, which is a function of course, the amount of capital per person. So in order to get sustained economic growth, first of all, you would need to have an increasing amount of capital per person, not just capital altogether. But second, this function is concave, because this alpha here has to be between 0 and 1. And with any other constant returns to scale production function, you're still going to end up with the same problem, that you will need an increasing amount of capital in order to get sustained economic growth. Of course, it's not worth accumulating an infinite amount of capital here, because capital is costly. The more capital you have to invest more. And the opportunity cost of that is consumption. Because of this exponent being less than 1, in order to have sustained economic growth, you would have to be accumulating capital faster and faster and faster. And that just isn't going to be optimal. So what do we end up with? We end up with the idea that there must be, for some reason or another, over time, a sustained improvement in the efficiency of capital and labor. In other words, this production function must also be a function of some parameter, I'm going to call it z for now, that increases over time and that we can think of as productivity. Now we're going to be able to say something more specific about the structure of these functions, the utility function and the production function. First of all, in the context of economic growth, we're very often going to say that agents maximize the log utility of consumption, where log here means the natural logarithm. Quite why we'll get to a bit later. Second, it can be shown that this production function, in order to be able to deliver sustained growth, needs to be such that productivity enters in a particular way. Productivity, in fact, has to be multiplying n, or some function of n. The specific production function we'll find ourselves looking at very often is going to be, sorry about that, this one. Why do we often want to look at Cobb-Douglas production functions like this one? Well, the reason is because in this case, as we can show now, the share of labor income is always going to be a constant. How do we see that? Well, let's say big Y is output, which of course equals this production function. The firms that live in this environment are going to be maximizing their profits, which are of course the output minus the wage and labor minus the rate of return to capital times capital. The first order condition with respect to labor of this is that the wage is equal to the marginal product of capital. Right, there is our first order condition. Now let's multiply both sides by n. Here we have n. This cancels out. And notice this is just output. Divide both sides by output. And you get that labor income divided by output is a constant. Bingo. That's something that matches the stylized fact that we had before, and that's what justifies having very often a Cobb-Douglas production function. So this is the production function we're going to use, and we're going to assume that zt, this productivity term, equals z0 times gamma z to the t. So there's some initial productivity z0, and then it grows by some factor gamma z over time. Very well. Now what we need to do is to try and express all of the variables in this problem in consistent terms, and by that I mean in terms of per capita variables. So aggregate variables will be in uppercase, per capita variables will be in lowercase. That means that little c of t is big C of t divided by the population little investment per capita will be equal to big investment, total investment divided by the population. The capital stock per capita will equal the total capital stock divided by the population. The labor input per capita will equal the total input of labor divided by the population, which of course will equal 1, since that is a labor endowment, and they don't care about leisure. And just in case, output per capita will equal total output divided by population. Great. So for this redefined problem, the utility function is the same. It's already in per capita terms. Next, we have to deal with this, the budget constraint or feasibility. And so let's just start by dividing everything by the population. Great. All right. This is clearly just little ct, and this is clearly just little it. For this, let's note that anything is the same as the thing to some power minus the thing to 1 minus the same power, which means that we can break this into 2 parts. There we go. Now let's examine these things carefully. We can extract alpha from here, as it's a common power, and we can extract 1 minus alpha from here, and as it is also a common power. And now we can see this is little kt, and this is little nt. So we're able to do this modification of turning the feasibility constraint into per capita terms with very little difficulty. Now let's turn to the capital accumulation function, and let's divide all parts of it by the population. Okay, here is little kt, and here is little it. However, in this case, we have to do a little more work. Multiply top and bottom by gamma n. Get that on the top, and here we just add another gamma n to the bottom. Now, this is small kt plus 1, capital per capita. And so we see that the capital accumulation function does not remain unchanged, because we have this extra factor here that is going to make, probably in a quantitative sense, a small difference, but nonetheless, it is a difference that makes this problem different from this problem. Great. Now the next problem we have is the following. Let's consider a situation that fits the data that we looked at earlier. Remember that we said that the growth rate of output of GDP doesn't seem to be changing very much over time. There's no trend upwards or downwards, they're just fluctuations around it. And right now we're focused on the trend, not the fluctuations. Now here's output. Now, since output has, let's call it fairly constant trend, it's going to be very difficult, if not impossible, for consumption and investment to have a different trend. If either of them had a different trend, the other one would have to have also a different and opposite trend. So if consumption trends upwards, investment would have to trend downwards. But if investment trends downwards, that's going to be a drag on growth here. Similarly, if consumption trends downwards, investment would trend upwards, and that would make this explode. So what it means is that whatever the growth rate of output is, consumption and investment are going to have to share that same growth rate, at least in the long run. Let's use the per capita version of the production function. We can take this, divide everything by the population. We know that this is going to end up being small k and small n. And this is small y. Now let's think about their growth factors. We're going to use g of y to mean the growth factor of output, g of k to mean the growth factor of capital, and g of n to mean the growth factor of labor. So this means that in order for this to hold all dates, it must be the growth factor of y equals the growth factor of z, which is of course gamma z, times the growth factor of k, call it that for now, and then figure out what it is, times the growth factor of labor per capita, which is 1, since each individual is endowed with 1 unit of labor, which does not grow. So this is a first equation that we have that pins down the long-run balanced growth factor of this economy. Next, since output grows by a constant factor over time, gy, in equilibrium, both of these must as well grow by the same factor. Why? Well, if this grew by a different factor, if it was larger, then capital would be growing faster than output, and that wouldn't make sense because n is constant. And slower would not make sense either for the same reason. So that means that the growth rate of consumption and investment has to equal this, the same rate thing as the growth rate of output. So that means that this is some number times this to the power of t. Now, since these two things, capital on a balanced growth path, must grow at some rate, they must of course grow at the same rate. In order for this equation to hold in a balanced growth path, it means that that rate has to be the same as the growth rate of investment, which is gy. So that means that all unbalanced growth path, the growth rate of capital has to be the growth rate of investment. And the growth rate of investment, the growth factor of investment, has to be the same growth factor of output. And that means, therefore, that the growth factor of investment equals the growth factor of output equals the growth factor of capital. Now we take this equation from before, and that means, of course, that this is the same thing as the growth rate of output. And that means that growth rate of output on a balanced growth path must be equal to this function of the growth rate of productivity. What's the economic interpretation of this? There is productivity growth, and what happens is that as there is productivity growth, there is more and more accumulation of capital. So increased productivity stimulates increased accumulation of capital. Next, what we are going to do is detrend some of these variables by this growth factor. And when we do that, you'll see why it is that that is necessary in order to make sure that we can solve our growth model using dynamic programming methods. Now for this, define the following variables. Define C hat as little c divided by g of y to the t. In other words, what we're doing is we're defining this c hat variable to be the deviation of consumption from its trend. Notice I put gy here because, of course, if output has a long-run trend, the trend of consumption and of investment would have to be the same. The growth rate of output will have to be, in the long run, the same as the growth rate of consumption and investment. And we can define the other variables similarly. So we could have I hat to be per capita investment. Detrended K hat is capital per capita. Detrended. N doesn't grow, so we don't need to worry about that. And Y hat is output per capita, detrended. Now what are we going to do? Now we're going to redefine our problem in terms of these variables. Let's start with the utility function. C is C hat times this, the growth trend, right? And notice, of course, that since we have log utility, we can separate this out. Right? Where we have C in these brackets and the trend in these brackets. And it should be clear that now we have a slightly stricter condition for this to make sense. We need this to be less than 1. And of course, we need separating the sums. We need this thing to be finite. Given that, we will have a perfectly well-defined utility function. And notice that this is actually a constant. And of course, the behavior of someone who has utility u is the same behavior as someone who has the same utility function u plus some constant. So let's just get rid of it. Next, what do we do with this constraint? If we want to put this in these terms, we need to divide through by this number. And we'll just have C hat I hat. Notice that ZT is just Z0 times gamma Z to the power of T. And also gamma Z to the power of T is just GY to the power 1 minus alpha times T. Capital here is the product of K hat sub T and its growth trend, because you can see capital, for this to hold in the long run, has to grow at the same rate as investments, and of course investment has to grow at the same rate as output. And you can see that if we bring this outside the parentheses, we have gy 1 minus alpha t times gy alpha t, which of course is simply gy to the t. So this cancels from the top and the bottom. And boom, we're done, almost. We're done with that constraint. The last constraint we need to detrend is this one. So divide both sides by gy to the t. This, of course, is k hat. This is I hat. And this is not k hat tomorrow. For that, we would need to multiply top and bottom by gy. The bottom then, of course, becomes gy t plus 1. And now this is k hat t plus 1. So after all of that, we've now reached the point where we can see how we're going to be able to use dynamic programming methods to look at this problem when there is productivity growth. We will be solving this version, which of course looks exactly the same as the original problem. The only difference is our population growth is functioning more or less as a discount factor. And we have these two multiplicative terms here in the capital accumulation function that keep account of the fact that, of course, capital per person and detrended capital are things that are not allowed to grow over time. They're supposed to be stationary, whereas their counterparts in the model, total capital, does, of course, increase over time because the population grows and because of productivity-induced capital accumulation.